All right, so welcome to our AARMS Scientific Machine Learning Seminar Series. It's a great pleasure today to welcome our speaker, Alison Malcolm from Memorial University, where she's an associate professor in the Earth Science Department. And she will talk about normalizing flows for seismic data interpolation. Take it away, Alison. Thank you.
All right. Thanks, Alex, and thanks everybody for being here. It's kind of fun to give presentations from my office. So as Alex said, I'm going to talk about using normalizing flows for seismic data interpolation, and this is joint work with a number of folks, but primarily Rajiv Kumar, who's at Schlumberger in the UK, and Maria Kotze, who's a former student of mine, who's now at Pangeo. And I'm also going to show some work from a few students, one of whom worked with Rajiv, and as well as Felix Herman, his supervisor, and a few who've been working with me. And so I thought that I would start kind of at the beginning, and there we go, and talk a little bit about what we're looking for in the subsurface. So we look for many different things in the subsurface. This particular work is motivated by the idea that we want to look for small changes in the subsurface. And why we might want to do that, there are many different applications that require monitoring changes in the subsurface. It happens offshore here in Atlantic Canada for oil and gas reservoirs as we look at how the oil and gas move and are produced from the reservoirs. It's becoming increasingly a part of our climate change mitigation strategies that people keep talking more and more about how one of the things we're going to need to do is to pump carbon dioxide into the ground and keep it there. And if you're going to pump carbon dioxide into the ground, the goal is that it stays there, and you need to monitor and understand that it stays there. So this is a pretty classic inverse problem. And the idea of, because what we have is data on the surface that we then want to use to understand what the subsurface might look like and how the subsurface might change. And in any inverse problem, an important step within that inverse problem is uncertainty quantification, which is understanding how well we know what we know, or how well we really know the answer and how many models there are that really fit our data. So I'm going to start today by kind of setting up an inverse problem, setting up uncertainty quantification, and then I'm going to talk about why we want to use machine learning for this, and then I'll talk about a simple example that we've done, as well as kind of where we're going forward with this in the future. So a very basic look at an inverse problem is that you have some sort of data, and you want to estimate the model parameters that give you those data. So a very simple inverse problem that you surely have all done is to take data and fit it to a line. There, in that case, your model is the slope and the intercept of the line, and your data are the points that you've measured that you're trying to then fit to the line. So we have two problems here. We have the forward problem, which is where we take the model and calculate the data, and the inverse problem, where we take the data and we estimate the model. In my particular problem of choice, the forward problem is to take a model of the subsurface, which could be the sedimentary layers in the subsurface, the layers of rock. It could be the fluids and where they've moved. And we calculate what data we would observe if we went out and did a seismic survey. And I'll tell you a little bit more about seismic surveys in a little bit. And then the inverse problem is to take the data from our seismic survey and calculate what has happened in the subsurface. And like I said, this is a pretty classic example. Seismic inverse problems are my cup of tea, but this is very similar to what is done in ultrasound. It's also done in very many different guises across all of science. But when we do this, what do we actually do mathematically? Well, we solve this particular optimization problem, or something that looks like this optimization problem. So the optimization problem that we're solving here is that we have some sort of model of our data, that's our F, and we apply it to our model. This is sort of set up as though it's a linear problem, which typically it is some approximation of a linear problem. And we're going to run an optimization to find the model that minimizes this expression here. And so the first term here, this is our data misfit. This is how well does our model fit our data. And then we have a regularization term that usually incorporates things we already know. So for example, in the seismic problem, we would always put some bounds on the velocity. It is between typically 1,000 and 4,000 meters per second, maybe 6,000 meters per second, depending on the problem that we're looking at. And so that is how, that's the optimization problem that we want to solve. Someone have a question? If you do have a question, please just pop in and say so. If you don't have a question, please don't forget to mute your microphone. Okay, so this is the problem we're trying to solve. And the way that we do this is we do some sort of typically local optimization. And so that means we start from a model, or maybe we start from a few different locations in our model space. So here's our model space. Here's our objective function. That's that function we were just looking at. And we try and minimize this function. So if we start at the green point, we get down here in that local minimum. If we start at the orange point, we get in the local minimum over here. Okay. But the issue with this, when we start to look for small changes and to recover parameters and understand their precision, is that all of these models might fit the data reasonably well. Your data have errors. Your objective function is not perfect. Your understanding of the physics you have to model is not perfect. And so the data that you have are going to have errors. And all of these models might be equally legitimate, equally valid. So what we really want to know is what is the probability that our model parameters are within a certain range. And we probably want to know about all of these local minima, not just the one that happens to be closest to our starting model. And this is where we get into uncertainty quantification and trying to understand not just what model might fit our data, but what range of models might fit our data. And we quantify this or turn this into an equation, typically using Bayes' theorem. And so what we want to know is this P of M given D. So that's the probability of a particular model being the true model, if you like, given that we have observed the data D. That's the probability distribution that we want to measure. And we know how to get this from the probability of the data given the model, the probability of the model, and the probability of the data. That's Bayes' theorem. Now, these guys all have kind of standard lexicon. And when we start to put in that standard lexicon, it becomes a little bit easier to see what we're actually trying to do. So our P of M given D, that's our posterior. That's what we know after we've done our experiment. We have our likelihood. This is essentially our objective function, okay? We have our prior, which is what we know before we start. So in the seismic case, that might be that the seismic velocities lie within a certain range, or the change happened. If you've been injecting CO2 into the subsurface, you know there shouldn't be any change before you started injecting. Those sorts of things go into our prior. And then we have the evidence, which is a normalization constant that we usually largely ignore. Okay, so when we start to plug these things in, so let's start the likelihood here. This is the likelihood we usually use in a sort of standard linear inverse problem. And it's very closely related to our original objective function. And in fact, the only real difference is that here we put in a standard deviation or a covariance of the data. And that covariance is there because we want to understand how the uncertainties in our data track into our final model. Now, one way to do this is to use something called Markov chain Monte Carlo. And I'm not going to go into too much detail on how this works, but the basic idea is that you start from your prior distribution and you start sampling all the possible models. And for each model, you evaluate the likelihood. You evaluate whether or not it fits your data. And in fact, and then by sort of continuing to sample this way, you end up with an estimate of your posterior distribution, or you end up with an estimate of the probability of your model given your data. Okay. And that's what we want. We want an estimate of our model, and we want to estimate the probability distribution associated with our model so that we can understand what plausible scenarios we have to investigate. Okay, and so to give you just a quick overview of what the Monte Carlo or the Markov chain Monte Carlo algorithm is, it's very, very simple, and this is part of its beauty. It's very, very simple because what you do is you start from your current model, which can be anything you want, and you perturb it a little bit. Okay, you perturb it just a little bit, you add some random perturbation to it, then you calculate the likelihood of that model. Then you investigate that likelihood and you see if this model is more or less likely than your previous model. Okay, and then you compare that to a threshold, and you either accept that model and move to that new model that becomes your current model, or you say, no, this model's not good enough, I'm going to stay with my current model. Okay, and there's a randomness to the acceptance and rejection, which helps to make sure that you try and sample all of model space. So then we're able to actually make these kinds of estimates. What's the probability that the CO2 has moved out of the reservoir interval? What is the probability? We can start to ask these kinds of questions. So that's fine. But now I'm going to sort of step more into the specific situation. And I'm going to give you a sense for why we don't use, or why we would like to do something smarter, and how machine learning builds into this problem. So to do that, I want to sort of explain a little bit about the seismic problem. So when we collect seismic data, and by we, I mean the companies that collect seismic data, what happens is there's a big ship typically. So typically this is done offshore. It can also be done on land. And then you replace the ship with a truck. There's a big ship and it tows behind it a source. In this case, it's an air gun, which is exactly what it sounds like. It shoots a blast of compressed air. And then a bunch of hydrophones, which are microphones that record sound waves in the ocean. And again, if you do this on land, you have trucks that shake to produce the source, and you have geophones, which are microphones essentially that we place on the ground or in the ground. The idea is that the waves go down and they reflect off the different layers in the subsurface, and then they're recorded by the hydrophones on the surface. We typically, though not always, use the acoustic wave equation, which you can see here, to model this experiment. So here's your source, F here, your displacement field, U, and this is the wave speed. C squared is the wave speed of the subsurface. Now, when we do this calculation, or when we apply this model, that means that what we need to do is we need to solve the wave equation for every source. We might have thousands of sources, and we may have a model that has millions of degrees of freedom. So it's a big problem, okay? And this is what we use as our model, okay? And the P here is just a sampling or projection operator that extracts the parts of the wave field that we will record at our sensors. So we keep it there to make our notation precise, but you can essentially ignore that part. Okay, so that's a little bit about how the seismic problem works. And now we set this up in, I mean, we saw this in many different ways, but one way we can do this is to set this up as the inverse problem that I've been talking about earlier in the presentation. But that's only part of the process. Part of there are many steps between collecting the data and getting the final interpreted product. And we typically would split these into, I would say, these sort of 4 categories. We collect the data, then there's some data pre-processing, and then we form an image. That's where the real inverse problem part typically comes in, and then we do some interpretation. So what I'm going to talk about today, I'm going to talk about how we work on how we've done this step, the image formation step, with Markov chain Monte Carlo. I'm going to talk about how normalizing flows take us past that and make things work a little faster. And I'm going to demonstrate the normalizing flows with one of our pre-processing steps, because in an ideal world, we would be able to translate our uncertainty quantification right from the data collection all the way to the final interpretation. And that is done to some extent, but it's typically done quite qualitatively. And especially as we start to use machine learning algorithms and so on in later stages, the quality control is really important. And it's really key that we understand what are the most reliable aspects of the model we might be feeding in to these final machine learning techniques. Okay, so the example I'm going to show you is based on a data set offshore Newfoundland and Labrador. It's not, well, I won't go into the details. We were not given specifically data for this, and so at some level the data are also simulated. And I'll try and kind of point that out as we go through, but just sort of understand that it's based on an oil field offshore Newfoundland and Labrador. And this is the work of my student, Stephen Lethbridge. So what Stephen did is he made a really nice velocity model. And this is harder than you think, but this is our best guess at the model of the subsurface. So the different colors that you see here are different seismic wave speeds. You can see that they range from about 2200 to 4700. That's the kind of typical range of the velocities offshore here. And you can see where the wells are and things, which is where there is oil production. We were trying to simulate the changes in the subsurface that come as you produce oil and try and understand the uncertainty as we estimate those changes. So here's what we estimated the change would be during production. You can see this is quite a small change. You've got a change in velocity of about 100 meters per second out of the 2,000 to, or say 3,000 meters per second of your kind of average background velocity. So it's quite a small change. And what we're going to try and do is we're going to try and recover this change by comparing two seismic experiments, one that happened before production started and one that happened after some of the production was already underway. So here's how we do this. The first thing that we do is we say, well, if we're going to do this with Markov chain Monte Carlo, we're going to need to sample a lot of models. We've got this teeny tiny little change right here in this whole background where we really expect very little change. So the first thing that we do is focus our efforts, and we use a local solver. So it's a way of solving the wave equation in a small subdomain that we've been developing over the past number of years. So we use that local solver so that we can shrink things down and work really in that small subdomain. So that's the first thing that we have to do. Yeah.
Yeah, I have a question. Actually, just go back to the previous slide.
Sure.
So the velocity here is like the speed of the sound waves through different mediums.
Correct.
And those vertical lines, are those supposed to be like the drilling shafts that you're going to see?
Those are the drilling shafts. That's correct. Yes.
And the horizontal blue line would be like the oil getting pumped out and the medium changing and the speed. Okay.
That is exactly right.
Okay, thank you. Thank you. I just wanted to be 100% sure. Thank you.
No problem. No problem. Definitely don't hesitate to interrupt if you have questions. That's great. Okay, so that's what we want to recover. We want to recover this blue part, and we're going to do this by using Markov chain Monte Carlo, and we're going to do it in a small subdomain because we expect that the change will be in there, and because we simply don't have the compute power to calculate to solve the wave equation in our million-degree of freedom model. So now if we step one step further and we start to say, okay, well, now we have this little subdomain, but actually we have to go even further. And this is kind of my point of showing this example. So this is what we would like to recover. Now it's a slightly different color scale, but there you go. It's what we would like to recover. This is our ideal recovery. But with Markov chain Monte Carlo, because you're sampling this large space, and you need to calculate many, many models to sample that large space, you run into the curse of dimensionality. So you just can't do it. You get too many dimensions to sample in, and you no longer, every dimension you add like an order of magnitude in terms of the number of models you need to test. And so this is the best we can hope to recover. This is 36 degrees of freedom. And I'm not going to go into the details of how we do the compression because I don't think it's that important. The key thing is we really have to compress this. So once we've compressed this, so now we're down to trying to recover 36 parameters. We can then do this. We can run our Markov chain Monte Carlo. We calculate about 500,000 samples. So we run the wave, we solve the wave equation in our little subdomain about 500,000 times. And this allows us to get some posterior distributions. So we're able to estimate, in this case, we looked at the average velocity change and we looked at the area of the velocity change. And it works fine. We end up with these very broad distributions. You can see it's definitely not a Gaussian centered on the true value, which would be your sort of typical uncertainty assumption. And we had to run 500,000 wave solves, and we were really only looking for a very coarse representation of our final model because we had to reduce our degrees of freedom so much. So this is where machine learning comes in, because MCMC is just too slow and it doesn't let us use enough degrees of freedom. And there are other techniques, and we've tried them, that let you use more degrees of freedom or fewer samples, etc., etc. But in our experience, there's a conservation of annoyance, and you end up with approximately the same amount of compute time. Okay. And so this is really a barrier, because if we want to do this for all of these arrows and really be able to follow the uncertainty quantification from the beginning to the end, we can't be doing millions and millions of calculations for each step. The calculations are too big and our model space is just too big. So this is how we come to the idea of normalizing flows. So what a normalizing flow does is it allows you to map a simple distribution, like a Gaussian, to a more complicated distribution, like the squiggle that I drew there. And it gives you an efficient mapping both ways. So I can take a sample of this distribution and figure out where it would be in this distribution, and vice versa. Okay? And this can be really powerful because it's easy to sample a normal distribution. No problem at all. We all know how to do that. You can define parameters on the normal distribution. What's the standard deviation? All of these things are well defined in a normal distribution. But it's not a great model, right? Even in our simple example, we had a non-Gaussian distribution with a mean that was not really close to the true value, or well, it was not in any case equal to the true value. So we would like to use this kind of distribution, and we'd like to be able to get them quickly. And so normalizing flows is also a way to make this mapping relatively quick, meaning that we can, we hope, be able to do this at multiple stages in the seismic processing sequence, or the seismic imaging formation sequence. Okay, so to give you a bit more sort of detail, so I think I've already told you this is the way that we're trying to move things through. And we thought we would start by looking at data pre-processing. Okay, and one of the data pre-processing steps that is easy to think about the errors that might be in is data interpolation, because we often have gaps in our data. Particularly on land, for example, there might be roads, there might be buildings, there might be ponds, and so there's almost always gaps in the data. And we usually fill in those gaps with some sort of an interpolation algorithm before we form the seismic image. But then we treat all the data the same. So even the data that we recalculated ourselves to put in the middle of some big gap goes through and has an equal weight in forming the seismic image. And that might not be ideal, especially when you're starting to look for very small changes in the seismic image. So, in order to try and do this interpolation problem, we set up a normalizing flow. And I'm going to go through in a bit of detail what normalizing flows are and how they work. But first, I'm going to sort of give you a sense for how this works for our data. So what you see in the top left is a subsampled seismic data set. So that's what you see right here. And then below it, you see a fully sampled data set. Okay. And for those of you who are used to seismic data looking a lot different, let me just kind of orient you that this axis is the source position. This axis is the receiver position, and this is a single frequency data set. So that's why it looks like a bullseye. So if you start from what we're going to do in our normalizing flow is we're going to start from our subsample data. Oops. We're going to start from our subsample data, and we're going to map it to a normal distribution. So that's our first normalizing flow, or our first flow. We're going to do the same thing with our fully sampled data. Okay, this is a machine learning algorithm, so we need to train it, and we train it on subsampled and fully sampled data pairs. Okay, and we take our fully sampled data and we map it to a normal distribution as well. Okay, and then we have a third flow that goes between, and I'll explain where this one comes from. But hopefully you can sort of see a path where we're going to go from our subsample data, we're going to go over to this normal distribution, and then we will go back to our fully sampled data set. And that's the sort of final pathway that we will use to go from our subsample data to our final distribution of our data. And because we're sampling this distribution here, we can sample the distribution of fully sampled data, or interpolated data, if you like, and that will give us, we are able to estimate a mean and something that looks like a standard deviation on this final data set, or this final mapping. All right, so how does this work? How do we map one distribution to another? Well, it's kind of fun actually to read about and to learn. And when I was learning about normalizing flows, one thing that struck me is that a lot of the conversation is about this equation here, and it's about reviewing the chain rule from calculus. And I found that frustrating, because to me this is the simplest part of the normalizing flow, because basically what we do is we change variables. We have some sort of target distribution, and we have an initial distribution, and we want to map between them. And so we have this mapping, and we have a change of variables determinant, okay? A Jacobian, basically. So that's what we have to do, but we have to ask, where are we going to get this mapping? And this is the key thing, because if I gave you that mapping, then of course you know how to go back and forth, but we're going to have to learn that mapping. That's going to be what our machine learning algorithm does. That's where our neural networks come in. That's where we do our training, is to learn this mapping. So how are we going to do this? Well, there are a number of tricks, and these tricks are really important to make this computationally feasible. And so I'm going to give you kind of an overview of these tricks, and then I'm going to show you how it works. And then, hopefully that gives you enough information to be dangerous, and you can hopefully dive into the literature and not get as stuck as I did on all of these folks explaining the chain rule. So the first thing that we do is we take this mapping and we split it into parts, okay? This is a sort of divide and conquer strategy. We're trying to get lots of little things to learn instead of one big thing. Then we give these parts a specific form, okay? So basically, each of these functions that we split our flow into has a set of variables it leaves alone, and a set of variables that it shifts and translates. So here's the description of that shift S and translate T. And so when you see that, or when you think about what the flow is doing, we're trying to learn a whole bunch of functions that leave some of our variables alone and shift and scale some of our other variables. That's how we're morphing one distribution into another. We're shifting it and we're scaling it. And we're doing it a few variables at a time. Now, why do we do it this way? Partly computationally, okay? Because we would like to be able to use a neural network to learn how to shift and how to translate, okay? And for our Jacobian, we really need that splitting, okay? And I think I'll talk about that in another slide or two, okay? So these are the networks we're going to train, our shift network and our translation network. And the way that we train them, right? So, I mean, again, as someone who comes from inverse problems, machine learning looks an awful lot like an inverse problem. we need some sort of loss function. Just like we needed an objective function for our inverse problem, now we need a loss function. And in this case, because we're trying to take two distributions and match them together, our loss function is essentially how close together we've got these two distributions. But then you need some sort of a measure of how close together two distributions are. And what we use, what is typically used in normalizing flows, we didn't come up with this, of course, is the KL divergence. So this is a way of measuring the difference between two distributions. And we're going to minimize this to find the weights in our network. Okay, so that's our goal. We're going to train two networks for each of our flows, and we're going to train them so that we're matching these two distributions to each other. Okay, now there's some key things that I told you I was going to sort of talk about. So there's an issue in this form here, which is that the x2 variables can influence the x1s, but not vice versa. And so in order to deal with this, we basically reshuffle the variables all the time. Okay, and there's a specific hierarchical network called a hint network that lets us do that, lets us change these variables. And we also need to combine our three sets of flows. Okay, and this is also done with the hint structure. Okay, and so for our input variables, we have our two networks that map from our initial distribution to our first latent space, or our first normal distribution, if you like. We have one of these for the model side, one of these for the data side, and then we have a connection between them. Okay, and we do this to give us our final conditional distribution. And I'll go through this again in a minute to kind of explain why we need this and how this fits into our Bayesian inference problem that we're trying to solve in the end. Okay. All right. So here's our Bayesian inference problem. We want to understand this conditional distribution. Okay. Just like we're looking at right here. Okay, where we have x given y, what we want to end up with is m given d. Okay, and that's why we need this connection to be able to go across from our subsampled data to the normal distribution associated with our fully sampled data. Okay, and that's what our sort of final target is when we map back through our whole flow structure. Okay, so to kind of step back a little bit and explain how this works for our problem, what we're trying to do is we're trying to take our subsampled data and map it to an estimate of our fully sampled data. So we learn these mappings, we learn how we get from these distributions, okay, and we do that with our shift network and our translation network, okay. So we've trained our two neural networks to go from here to here, to go from here to here, and to go from here to here, okay? Then we come with a new sample. With our new sample, what we do is we go from our subsample data to our normal distribution over here, okay? And this is a joint distribution because it depends on both our subsample data and our fully sampled data, okay? So if you like, this is our model, this is our data, because it depends on both of these. This is a joint distribution. And what we do then is we fix the data. We fix the subsample data. And now within this distribution, we can sample different versions of the fully sampled data that match our subsampled data. So if you think about this in terms of two parameters, we fix x1 and we sample over x2. And this gives us a range of fully sampled data sets that fit our subsampled data. So it's giving us the same kind of information as our Markov chain Monte Carlo, we are sampling our model space for all of the models that fit our data, but it's doing so in a much more efficient fashion, because instead of having to essentially check every model, once we've done our training, once we know how to get from our subsample data to this distribution here, we can just apply these neural networks. And so we're shifting a lot of the burden to the training phase instead of having to do this for each new data set. It's also simply faster, and I'll give you a little more details on that in a minute. Okay, so this lets us map our fully sampled and subsampled data sets to a normal distribution. Then we come back to our fully sampled data set. So here's our initial subsample data. Here's our fully sampled data. And here are samples that we've drawn from our distribution, from our final distribution that we're trying to estimate. So if we come back to this figure, these are samples where we've gone from here to here and then back over to here, okay? And that gives us, here you can see 4 examples of the interpolated data. And of course, we can do this not just 4 times. If we're interested in characterizing the range of data models that fit our data set, our subsample data set, we can do that, and we can calculate a mean model, and we can calculate something that looks like a standard deviation. Now, I'm being careful to say something that looks like a standard deviation, because it's not actually a standard deviation, because we're not actually sampling a normal distribution, right? We're not taking the standard deviation of this distribution. We're calculating a variance, if you like, or something of this distribution, okay? And this is not a normal distribution. And so we can't just take the standard deviation and assign meaning to that. But it does give us a sense of the data weights. And when we look at it, it makes some sense. You can see in the original data, you can see you have a gap here. And if you look over here, you can see you have a high standard deviation here. You have a high error. You have a lower confidence in that data set. And so our goal is to then use this as a way of mapping the uncertainties into the next stage of the seismic processing. So just to give you a few details for those that are interested, we used 20,000 training pairs, and we trained for 12 epochs with a batch size of 64. You can see our loss function and how it evolves over those epochs. You could perhaps argue we could have gone a little longer, but certainly we're past the point of fast decrease of that function. To set up our training and testing data, so you see our data here. To get our subsampled data, we started from perfectly sampled data, and we randomly dropped that out. That's say a kind problem, or it's an easier problem than if we were to, for example, take out the middle third or something like that. And it's both situations arise. So both situations could be deemed more realistic. Now here's kind of an interesting part from the computational side. We had about 30,000 degrees of freedom. So like 1,000 times what we had for Markov chain Monte Carlo, almost 1,000 times. And we did 10,000 training iterations. And now this is a different problem and so on, but there's no way we could do Markov chain Monte Carlo for this many degrees of freedom. And 10,000 models would be nowhere near enough to do that kind of sampling. And so this is what led us into normalizing flows to begin with, and it's certainly clear that this is a much more efficient way to sample our solution space and to understand the associated uncertainties than running straight through with Markov chain Monte Carlo. So we chose normalizing flows because they can handle a high dimensional space. I didn't really emphasize what makes them so computationally feasible. I'm happy to address that in the questions if you would like. But basically, the functions are chosen very cleverly to make this turn out, and not by us, by others, but works very well. We don't need prior knowledge of the distribution. We can just essentially put in our data in their labels and expect things to work out. And we get a reliability measure. It's not an error bar. This is a downside of normalizing flows. From Markov chain Monte Carlo, we really get an error bar. But from normalizing flows, we get kind of more of a, we call it a reliability estimate, but we get a somewhat undefined quantity that describes the spread in our data. And so that's a subject of future work that we're thinking of moving forward. We want to understand what the meaning of that standard deviation really is. We've been talking about using the central limit theorem to see if we can train many times and explore that. We're trying to relate the standard deviation in the latent space to the standard deviation in our space or in our true space. Because we really do need to understand this, and we really need to come up with some measures that make a little bit more sense for our sort of shifted distribution. So we need to be able to estimate those measures as well. And we're still working on moving towards this kind of goal of translating our uncertainty quantification from the beginning of the process to the end. I showed you an example of using this in data pre-processing, but we haven't really talked about image formation. We're working on that now. I have a student who's working on that right now, trying to understand how we can go and take the output of these normalizing flows and translate it into another set of normalizing flows that do the uncertainty quantification in the image formation step, like we did in the Markov chain Monte Carlo example that I showed you at the beginning. So thank you very much for your attention. I'm happy to answer any questions that you might have. And I'd just really like to express my gratitude to the sponsors of the work and to you guys for being here and listening to me talk for whatever that was, 45 minutes.
Thank you very much, Alison, for this very nice talk. We have plenty of time for questions. Are there any questions? We have a fairly small group. You can simply unmute yourself.
I have a question. When you say like image formation, do you mean like drawing one of those cool cross sections with the different layers of stuff?
Yes.
And does that seem close? I mean, is there enough data to actually like build one of these things from these seismic measurements? I mean,
oh yes, absolutely. I mean, so I'm not going to tell you that it's trivial, but it is done. We know how to take the data and form an image. The uncertainty quantification is a little bit, it's done as well, but it's typically done in a more ad hoc way. And so, we're working on doing it in a more determined way or more quantitative way. But certainly we can form images from seismic data, and they don't look like, let's see if I have, I'm trying to think if I have a reasonable seismic image in here. I think that I do not really. Yeah, because that's not. But so this is our initial model, but this would not blow me away as a final image of the change. And again, this is our input model, and this is higher resolution than I would say we would get by simply solving the inverse problem and forming an image. But it's not crazy, and this was made from seismic data. My student Stephen processed the data and picked events in the data and used those to come up with a model like this that fits the data, to within some level of error. So yeah, it's definitely possible.
Other questions? I think there is a question in the chat.
Oh, is there?
I think somebody just raised that they want to ask a question.
Oh, okay.
I think it was Aida Assad. Is that right? Do you have a question?
Hear me right now?
We can hear you, but there's a lot of echo.
Is it okay now?
I did not hear much of that.
Okay. I wrote here because it's echo. I don't know what's the problem here.
I'm sorry, I didn't quite catch that.
Do you want to type your question in the
Yeah,
chat?
maybe type.
If the audio isn't working, just type it in the chat.
Ida is also my student, so we can also always talk later if we have too many technical difficulties. Yeah, I mean, that is the key idea, that you use sort of lots of functions to do the approximation. And, you know, I didn't want to go into too many details because I do think it's quite complicated. It's clever, but it is quite complicated. And yeah, it is so that you can describe complex functions. And so one of the sort of clever ways is that the way that the normalizing flows sets up this function here, because the computationally challenging part here is actually calculating this determinant. Because, you know, that's a matrix, and then you have to take the determinant of the matrix. But the way you set up these functions, that determinant becomes a lower triangular matrix. And because it's a lower triangular matrix, the determinant is now the product of the diagonals. And because that's way less calculation, right? You only have to calculate the diagonals now. You only have to calculate the derivatives on the diagonal. And that is what makes them computationally tractable at all, because otherwise you've got so many variables to fit. But this kind of clever setup, and then you combine that with these hint networks that keep reshuffling your variables so that it's not like, you know, x1 can influence x2 through 20, but x20 can never influence anything, because you're constantly reshuffling so that, if you like, every variable gets a turn at influencing every other variable. And so it's the combination of those two things that make this kind of very complicated structure feasible and useful in the end.
Oh, can I ask a follow-up question then?
Sure.
So basically, this isn't backpropagation. This is something different, right?
So you're going to have to tell me what you mean by backpropagation, because I think it means different things to different people, and I just want to make sure that we're talking about the same thing.
That is an excellent point. So you have some kind of loss function.
Yep.
And you have some training data, and you have some parameters, and those are your variables. And
Yep.
you want to wiggle around your parameters to, you know, have the loss function as low as possible.
Yep.
And for that, you calculate a gradient of the parameters, and you poke them in the right direction.
Yes.
And, you know, I mean, this is it's like standard neural network vanilla kind of things. Yep. And so your, you know, your layers are a composition of functions, like you have fk up to f1. And backpropagation is basically, you know, you calculate errors at each step, and you can push them back in the network.
Yes.
And calculate your gradient that way.
Yes.
But this seems different. You're flipping things around to get triangular matrices, and it's not the same thing.
No, it's not the same thing. And
Okay.
I actually think that's the trickiest part about normalizing flows. And I'm not even 100% convinced that I completely understand that. But the key thing is that you're training essentially 6 neural networks, and those are trained in the normal way. Mm-hmm. But it's the connection between them or the connections between them that use this very specific functional form so that it's invertible, and it has this lower triangular Jacobian, so that you can keep calculating that change of variables, because you have to calculate that change of variables, then you calculate your loss function, then you undo the change of variables, and then you send that back through each of your networks through your backpropagation. Mm-hmm.
Okay, yeah, thank you.
No problem. I hope that makes it clearer.
Well, it's clear that it's not as clear as I thought it was. It's not clear, which is cool.
The other questions? So maybe then I can ask a question. I mean, you mentioned you're solving an inverse problem, but you're solving an inverse problem for a process where you actually have some idea how the underlying equation should look like, right?
Yes.
You have sort of governing equations, and they don't seem to factor in at all, right, in your machine learning solution. Have you, I mean, I know it's like some people call this physics-informed machine learning or so. Have you
Yeah.
looked into this at all?
I
Is
mean,
that
I've
sort
looked
of,
into it a little bit, and other people have certainly used it. I would say that so far, most people have used it for what I would describe as the simpler problems in seismic imaging. So,
Mhm.
like, people have used it for calculating travel times with the Eikenel equation.
Mhm.
I've seen quite a bit of work on that front, and I think it's super promising, especially for the forming of an image part. Because then, like you say, we know what the physics is.
Mhm.
And there's also, I've seen some work, and maybe you might know more of this, and this is something that I'm super interested to learn more about. But like, one of the problems in seismic imaging is that we know the physics, but often we can't afford to calculate the correct physics, or our data don't really quite fit the physics. Like for example, like we use an acoustic model, okay, but believe it or not, the Earth is not a fluid. And so, we should use actually probably a viscoelastic model is what we should be using. And so, but like to do that calculation is so much heavier. And so I think there's a place for some of the physics informed neural networks in there as well, where it's like it's physics informed, but that it's not physics strictly adherent. Let's put it that way. Because because sometimes our data really do deviate from the physics, and we may not even know the exact physics that they're obeying.
Yeah, that's a good point. And like you said, if it's a really complicated model, it's actually not so trivial to train them stably, right? To sort of enforce sort of the equations,
Yep.
the data, and sort of everything at the same time and get a stable solution. That's probably
Yeah.
still a bit out, maybe. Yeah.
Yeah, and I think the other thing that, like, and this is, to me, this really speaks to the connection between machine learning and inverse problems. There's a nice paper from the University of Calgary where they basically show that if you train a recursive neural network to solve the wave equation, then when you do your back propagation to adjust your weights, you're actually doing exactly the same thing that we do in full waveform inversion, which is where we back propagate the data, and we use that to calculate a Jacobian and a model update and so on. It's actually the same, and the weights of your neural network end up being your velocity model. And so the only difference that they found between the two processes is the efficiency of the optimizer. And so there is sort of a connection sometimes between other neural networks or other machine learning algorithms and the underlying physics, even if you don't necessarily describe it that way. That connection is there. So I think that's really interesting. And that's my favorite part about machine learning, is when the machine learning algorithm is able to like teach us the physics. That's my favorite part.
Yeah, that's awesome. I would have one more follow-up question. Actually, sort of a separate question. I mean, basically, okay, so you solve your problem using normalizing flows, and you talk about, yeah, sort of this slide, right? You have this Kalbeck-Leibler divergence, sort of trying to match these distributions. But there is other sort of generative machine learning models out there, right? Like one that uses the KL divergence would be, for example, variational autoencoder, or sort of maybe more, I guess, prominent these days would be generative adversarial networks. I mean, they seem to do something similar, right? They take basically something that's your data distribution, maps it to something that's meaningful. Have you looked at all into sort of training an autoencoder, or like even a GAN, or like what do you, because I mean, you're training, you said 6 separate sort of neural networks here just to get this sort of quite specific form that sort of makes it easier for you to solve your problem. Like, have you considered sort of what would stop you from using, say, a standard variational autoencoder or generative adversarial network for your problem here?
So we have not specifically looked into that, but there is a nice paper from a group in Edinburgh. Andrew Curtis is the professor, and I can't remember the student's name, where they actually compared Markov chain Monte Carlo, variational autoencoder, and normalizing flows for a travel time tomography problem. And you know, basically, it's very much a kind of all roads lead to the final distribution, and they use, if I'm not mistaken, they use MCMC as kind of the gold standard, the truth, and they find that they don't get kind of exact agreement, but that they do get, which of course you wouldn't expect, but there are definitely differences. But they found their conclusion was that, and I hope I'm not misstating this because it's been a while since I read that paper, but their conclusion was that normalizing flows kind of won on the combination of efficiency and reproducing a distribution similar to what they got with their Markov chain, their kind of brute force uncertainty estimation. So I think that there's definitely room to explore those techniques more and to kind of understand how they apply to this problem in more detail. Because I'm not convinced, like, you know, someone asked me, you know, well, should I go learn normalizing flows now? And I'm like, well, you know, there's a bunch of different ones, and I'm not really ready to throw my hat firmly in one ring. Because I think that I think that to a certain extent it's sort of what you prefer is also, like, it's also okay. I don't think there's a clear winner in this particular problem.
Thank you. Any other questions? If there is no more questions, then we call it a day for this seminar. Then thanks once again, Alison, for giving this very nice talk, and thanks the audience for attending. And fingers crossed, if all goes well, there will be another seminar next week. So wait for the announcements through the mailing list. And then hopefully we'll see you all soon. Thank you.
Great. Thanks, Alex.
Bye now.
Bye.
Thanks. Bye.